Anyway, on to this evening's entertainment. I'd like to introduce sorry, entirely my problem. Dr. Danny Clark Lowes. Is that how you pronounce it? It is, there you go. And he did his undergraduate in Cambridge, and then did his PhD at IC, hence the connection. And then since then, pretty much has been consulting. All around the world, but really focusing on North Africa and producing a lot of material on Libya and all the way along there, and publishing papers and all sorts of things, doing really well. So you ask, why is he talking about the Himalayas? Well, he has been climbing in the Himalayas. So this is a sort of what have I done on my holidays, except that there's also a geological field guide to the Himalayas, which has been published by Danny. So very well done. And I think I'll just hand it over to you to take us through the Himalayas. Thank you.
Thank you very much. Thank you. Do you want to turn this on? Or have you already done so?
Yes, it should be on.
Okay, very good. Thank you for the nice introduction. And I'm going to tell you something about what I've learned about the geology of the Himalayas in the course of various trips that I've made. So I hope you'll be able to read the screen. There's a great deal of compression going on in the Himalayas. It's a continent-continent collision. And so in consultation, it was decided that this should be a compressed account of the geology of the Himalayas. We'll see how compressed we can make it. This mountain here is Fishtail Mountain, Machu Picchu, and it's a view from Pokhara where, in my opinion, all the best Himalayan trips start. The mountains around are the Annapurna Mountains. There's 4 of them, Annapurna 1, Annapurna 2, 3 and 4. And the highest is number 1, and it's just visible here. And it is the 10th highest mountain in the world at 8071, I think, meters, just over 8,000 meters. Here we have a digital elevation map of southern Asia, which captures the character of the Himalayan mountains and the region quite well, I think. This upland area here is the Himalayas and the Tibetan plateau lying behind it. For the scale, we have 2,300 kilometers from Pakistan up here in the northwest, right through to Myanmar here in the east. So that's 2,300 kilometers. The Himalayan mountains lie on the southern side of this vast plateau, which is 1,000 kilometers from south to north, with the Tarim Basin lying to the north of that. So the talk is mainly about the Himalayan mountains, but the geological story is about really all of this. In the foreground, actually in the foreland basin, you have the Ganges foreland basin here, running along more or less where the Ganges River is. And that's a depressed piece of continental crust on the south side of the Himalayan mountains. It's the highest and the youngest and the biggest and the best mountain chain in the world. And it's extraordinarily high. All this grey area here is over 5,000 meters. And if you speak to a physicist or a rheologist, they'll say that's unstable. You shouldn't have a lot of land above 5,000 meters. It should naturally fall back. The continents are lighter than the oceans, but and so they can rise above them, but they should not rise that high. So something dynamic is going on which keeps this plateau so high. Here's a view from the south, looking more or less from Gujarat, looking across to the mountain chain. Some people have described it as one of the most spectacular views in the world. We're looking across the Ganges foreland basin into the first mountains, which are the Siwaliks. And the Siwaliks are tertiary, they're very young, they comprise fluvial sandstones, sandstones that were shed from the rising mountain chain. Beyond the Siwaliks, you then get into the Himalayan series, which we will look at in due course. This is the main frontal thrust of the mountain chain at the foot of the first escarpment and the foot of the Siwaliks. And so the best place to find out something about the geography of the Himalayas is to go into one of the Buddhist temples. And I found this on the wall, this wonderful painting, and it's extraordinarily accurate. Here is the mountain chain. To the north of it is the plateau of Tibet. Here is Lhasa, I beg your pardon. Here is Mount Kailash, the holy mountain of Tibet. And from it is flowing a vast great river which cuts down through the mountains and flows down to the south, actually into the Ganges basin. Well, that's what the Indus River does, although not following quite that route. And so to look at the northern area, here is Lhasa and the Potala Palace. And here, north of the mountain chain, you see, you have lots of yaks and yak trains and Buddhist temples. And south of the mountain chain, you are into more temperate climate, and you have lots of terrace agriculture, and you have right down in the Terai region, which is down on the Indian plains, you have elephants, and there's just a lion in there. There are more of these Buddhist temples. Anyway, it captures the character of the mountain chain. The first real understanding of the mountains came about as a result of the work of the British Raj in India and the East India Company. The East India Company established the Great Trigonometrical Survey, which was to map out India, Greater India, as it was then. Here's a baseline survey being undertaken in Calcutta in 1832. They used two different methods to make maps. They used the triangulation standard surveying method, and they used sextants for positioning using the stars. And they would establish positions using both methods. And if they contradicted each other, one had to try and work out why it was. Well, it was understood that if you're adjacent to a major mountain chain, or any other very large body which has a gravitational pull, it'll affect the plumb bob of the sextant. And that's what was happening. So it was appropriate, therefore, to make an adjustment for the gravitational pull of the mountain chains. And they did that using a figure that they thought would be appropriate, because they assumed that the mountain chain was underlain by very dense rocks. Well, it didn't work. So the Astronomer Royal, who was a man called Professor George Airy, he thought, what if the mountain chain is underlain by relatively light material, granitic material, material with more silica in it? And indeed, when an adjustment was made along those lines, all the measurements matched. And it was a result of that that his theory of isostasy, the Airy theory of isostasy, was worked out, that you can have a large lightish body in a denser body, and it will find an equilibrium. And we're all familiar with that from icebergs. And with an iceberg, it's 1/8 above and 7/8 below the water. And those are the sorts of proportions that are appropriate in the mountain chain. So for the Himalayas, Everest is 8,849 meters. It's gone up since you were at school by 1 metre. And so that's nearly 9 kilometres above sea level. So you've got to multiply that by 7 to get what the depth of the root of the mountain chain will be below, so some 75 kilometres below. So that's a really exceptional geometry, because the continental crust is normally about 35 kilometres thick. So we're talking about a very exceptional situation. And that was understood by that man, Professor George Airy. The next thing that happened was that it was decided by a man called Sir Richard Strachey that we should have a geological transect through the mountains. No one had done it before, so he went to his superiors in the East India Company and said, I'd like to make a geological transect. And they said, well, you'll have to take time off. He wasn't going to be paid. He was paid to build canals. This was before the age of steam, so canals were the best way to transport things. I suppose actually it was the age of steam, but they hadn't introduced steam into India at that stage. And so in 1848, he made this transect. Now, this is a photograph of the cover of the paper that he wrote, a rather elegant front cover that I couldn't resist showing to you, although you won't be able to read it. The transect was made just northwest of the present boundary of Nepal, through what is the Indian Himalayas. And he went up to Mount Kailash, about 200 kilometers through the mountains, 200 miles actually, 320 kilometers. Now, I've stretched out that cross-section and presented it from south to north. And again, you're going to find it difficult to read it, but let me just explain. He understood the basic structure of the Himalayas. So here we go. This is what you came to hear. You start off in the Sewaliks, which we've already mentioned. You then go into an area of metamorphic slates, mainly without fossils. There are some, but mainly without. And then you rise up to the highest mountains of the chain, which he called the crystalline schists, which was quite right. They're schists and gneisses and some granites. And then he came down the far side. He went over a pass that was over 5,000 meters. He had a team of about 40 people with him, porters and horses and yaks and so on, people to operate the kitchen. And he came down the far side and he discovered a complete succession of Paleozoic rocks. The Cambrian ones are a bit odd, but from the Ordovician on right up to the Cretaceous, it was a succession that you'd all recognize. So in the Ordovician, you had limestones with fossils in them. When you got to the Permo-Triassic rocks, they weren't so much red beds because they were a bit more distal. So the whole succession was fairly distal, fairly marine. But the succession that you had was one that you would recognize, and one which William Smith had published already in his famous map of the geology of Britain, where if you look at it, you'll know that cross-section that goes from Wales to London, and it shows the whole succession from the Welsh Paleozoic, lower Paleozoic rocks right up to the Tertiary. And so he must have been rather astonished and amazed, and found a great collection of fossils, which he sent to friends of his in England, and established this complete succession. He was an interesting man, canal builder to start with, a military man, a soldier. He went on to be a member of the cabinet that governed the whole of India, and he also in his spare time he managed to be the chairman of a railway company. He was married to Lady Strachey, who gave him 13 children, 10 of whom survived. One was Lytton Strachey, the famous critic and member of the Bloomsbury set, and Pippa, a famous suffragette. A very interesting man. He went past Nanda Devi on his traverse of the mountain chain, and he will have reflected as he looked at it, because he's looking at it from the east, that these beds are all dipping down to the north. And that's one of the major characteristics of the mountain chain, which I forgot to point out to you, but when you look at his cross-section, he caught that. He caught that all the beds, perhaps we'll see it, all the beds are dipping down to the north, a very major characteristic of the mountains. But what he noticed most of all was that in the area just to the north of Dhaulagiri, which is just to the west of the Annapurna Range, which I told you about, and is the 7th highest in the world with that height there, he found these incredibly folded mountains. And this one's folded round that way, this one's folded round that way in a ridge that's in front of that one. There's a major fault up there, and he realized that whatever else was going on in these mountain chains, there must have been major compression. And that, I meant to show you this slide better because you can see rather better some of the structures in it. So he realized that there was major compression. And a chap called David Green, who I think he's going to lead a field trip for you to Somerset, and published a book just a short while ago about the quantox. And in it, he was explaining in an early chapter how mountain chains formed. And I thought this was a rather neat little diagram. It doesn't capture all the characteristics of the Himalayas, but it does get some of them. So here we have India, continental block. Here's Asia, another continental block. And they are forcing towards each other. They are moving towards each other, and they are squeezing the rocks that are between and folding them into amazing folds. Now, this presumably is roughly what Richard Strachey thought was going on. David Green's got it right, that we've got 1/8 above sea level and 7/8 below sea level, a major route to the mountain. Some, he says, 80 kilometers. That's about right. So the continental crust is relatively light, and the lithosphere here, the lower lithosphere, is relatively dense. And so this is behaving like an iceberg, and it's obeying the laws of isostasy. Okay, change. Let's move on now, nearly 100 years, and talk about thrusts. I've already given you a hint. All of those steeply dipping surfaces to the north are all thrusts, although Richard Strachey perhaps didn't realize it. But John Auden did, and he went to the Himalayas because he wanted to climb Everest, which was the sort of thing to do in the 1920s. And he didn't get to do that, but he did get to make some wonderful geological cross-sections and geological maps. And in this one, you can see that there's a thrust there. The geologists, by now, there was a Geological Survey of India that had been operating for 80 years, and he was the last British member, the last Englishman to join the Geological Survey of India, and the last Englishman to leave it. He realized, mapping the area around Simla, Kroll it's called, that you had these thrust faults. So that green layer has been reversed and forced up in a southward direction. So these are the north dipping surfaces. They're thrusts, so they're verging to the south. The next person I'd like to tell you about is Ganser, Augusto Ganser, professor of geology at the University of Zurich. And on his expeditions, he would always disguise himself so that he could get into Tibet, and disguised himself as a Buddhist. And here he is in his outfit. He made this cross-section, published in 1964 But he worked from the 1930s onwards in the Himalayas, in Tibet and in India and Ladakh and so on. And here we have the same succession that was recognized by Strachey, and they've got names now. So the Lesser Himalayan series, the Greater Himalayan series, which are the crystalline ones, schists and gneisses, and then the Tethyan Himalayan series up here, which is the whole Phanerozoic succession of sedimentary rocks, unmetamorphosed, with quite a good fossil record. Here he is, sitting with colleagues on a field trip. He was, in his mapping, you see he's recognized these strong north dips, and that many of them, as indicated here, are thrust faults. But how? How do you do it? How do you shift large blocks of rock, tens of kilometers, on very low angle thrust plains, and push them uphill? How do you do that? Well, he didn't know. But someone who did was a man who worked for Shell. And we'll come to that in a minute. Just a bit more about this Tethyan Himalayan series. Within it, Ganser recognized these naps because this is a famous one from the Alps. It's the Morkles nap. I don't know how you pronounce it really, but it's a dramatic feature there, hundreds of meters high. And also he saw, more naps. That mountain there with this fold is some 2 kilometers from the base of the fold to the top. It's a 7-kilometer mountain, Nilgiri North. And here's another view of it, near Johnson, in the northern Kali Gandaki River, which some of you know. Now, the chap who worked out how these thrusts work was a man called M. King Hubbard. He was always called that. And he was working with Shell. And he was a geologist and physicist. And he realized that if these rocks were being moved at considerable depth, the movement would be facilitated by very high fluid pressures. Being an oil geologist, he was looking at fluids in rocks and look at the pressures of those fluids. And he cracked how this could happen. And the last bit of this conundrum was resolved. In the cross-section that Mike Searle drew, south from the Dhaulagiri mountain, he went into much more detail about the various different thrusts and named all the different units right up to the Dhaulagiri mountain. This is, if we just go back, it's a slightly sort of fuzzy picture. I took the same view. This is my picture, and you can see some of the thrust in there, although I think actually you can see it rather better in here. But this is how it's all been mapped out. Now, Mike Searle is the professor, or now emeritus professor of geology at Oxford University. He's written a book called Colliding Continents, and it is basically the Bible on the geology of the Himalayas. He published it in 2013. Previously, it was Ganser, who I've mentioned to you, the Swiss geologist, who published the geology of the Himalayas in 1964. Mike Searle's now involved in trying to rewrite Ganser's book, and it's said to have a comprehensive account of the mountains. And so, this is a modern cross-section through the mountain chain, and I've already described the Sewaliks, and we've described some aspects of the Himalayan series and how they were first worked out about the thrusts and the folding. I want now just to move a bit further north. It's actually a cross-section through Kashmir and Ladakh, and it's the most suitable cross-section to illustrate the whole story. So let's now look at what's going on here, which is a very interesting part of the Himalayan series. There's a fault here, which is a low-angle normal fault. The sense of movement on it is there, so it's a normal fault. But normal faults should go at 60 degrees. This goes at about 30 degrees. So I like to call it an abnormal normal fault. It's called a detachment, and detachment is quite common in the Himalayas. It's probably been, almost certainly been, a thrust fault in the past, and its sense of direction has changed to a normal fault. And the rocks above it, remember, they weren't folded like this at the surface. They were some 10, 15 kilometers below the surface, 20, 25 kilometers below the surface when they were folded like this, and when they slipped on this surface. And the orientation here is quite different from what we saw further south. Further south, all the thrusts were verging to the south. The folding sense is towards the north. So it's a very profound change, this position. And it's where we come into the sedimentary rocks. In actual fact, the reason it's so abnormal is that it's not so much that these rocks moved down, it is rather more that these rocks moved up by a process called channel flow, which we will come to later. Just a few more examples. There's a fault here called the Lupra fault. This is the Lupra fault. There it is in an interpretation of this photograph. And all these rocks are upside down. The fossil record, it's through the Jurassic, fossil record shows that they are upside down with the most amazing deformation in there. And the interpretation, therefore, is that it's on the underside of a large recumbent fold. You remember those? We saw them here in this cross-section. So that pattern there is repeated further north in the Jurassic, and this is an example of it. And here, again, I've switched Nilgiri round. I've reversed it in order that you can see north on the right. In all my diagrams, I put north on the right. So here is this big recumbent fold matching that one there. So these are the characteristics of the Tethyan Himalayan series. And I'll tell you later why it's called Tethyan. But look at these amazing folds and deformation. This is Dhaulagiri, which you're perhaps getting familiar with by now. And as you go to the northeast, you come to Kuchi, and amazing folds in there, picked out by the snow. These, I mentioned already, lots of fossils. So the fossil evidence is very important. And where best to start than at the top of Everest? At the top of Everest, you've got crinoids in the Ordovician. So it was known that you could get marine fossils high up in mountains. Darwin had described it in the Andes, and the Chinese had reported it too, some 2,000 years before. But this was rather exceptional, that in the highest mountain on Earth, they were finding these crinoids. And it was Noel Adel, a geologist, on the 1924 Everest expedition, where Mallory and Irving were lost. And arguably no one knows yet whether they got to the top or not. But it was Odell who wrote, who looked through his binoculars, his telescope, and he said he saw Mallory and Irving going strong for the summit on the second step. So we know now that these mountains have been, the rocks at the very highest of the mountains have been under the sea. And the crinoids that were found high on the mountain were disaggregated crinoid stems, but this is what a nice intact crinoid looks like. The next thing is about the Permian. And it was one of the geologists with the Geological Survey of India, a man called Henry Medlicott, the steam age had arrived. Steam engines were the thing. And the survey were required to find lots of coal to operate the steam engines. So off he went, and he mapped out the coal, actually not in the Himalayas, but further south in India. And he got interested in the fossils that he was seeing, and he found this Glossopteris Permian fossil, and he discovered through his researches that this fossil, this relatively rare extinct fern, Glossopteris, had been reported in South America and in Africa and in Australia. And so it was he who came up with the idea of Gondwana, and it's named after a tribe in central India. And so the concept of Gondwana land was established. But how did these rocks in the Himalayas with Glossopteris in them get north of the equator into their present position? Well, they talked, of course, about continental drift, but they didn't really understand how that could happen, and the physicists were most insistent it was completely impossible. So Medlicott reported and built up information which suggested that India came from a continent far in the south, and there was other evidence by Du Toit about there being glacial deposits in the Permian in all of these countries too. So this is a reconstruction of how they thought it was. The next fossils to talk about are the ammonites found in the Jurassic. And all along the Kaligandaki from Johnson up to Kakbeni, you can find these, or you can buy them from traders, or you can go up to the Giula and find lots of broken bits of ammonite. These are from the Spiti Formation, or Lupra. That fault we looked at before was Lupra, it's all the same place. But the Spiti is a general term throughout the Himalayas for these Jurassic limestones containing ammonites. They're also called shalligrams. They're considered to be religiously important. Now, they've been identified as coming from the Tethyan Sea. And the Tethyan Sea was defined by a chap called Edward Suess, I think that's how it's pronounced, who was an Austrian geologist working mainly on the Alps. But the story there was the same, that the collision had closed an old ancient ocean. And he called it Tethys after the Greek goddess of the sea. And so it's possible to put together a bit of a story about the Himalayan series and where they came from. So the Tethyan Himalayan series, that's TH here, came from the passive continental margin of Gondwana. The next one behind that is the Greater Himalayan series. It's in there, GH, Greater Himalayan series. That came from the territory of Gondwana, which was more into the hinterland of this ancient continent, which turned out to be rocks about 1.5 billion years old. And the next lot is further into the hinterland of Gondwana, are the Lesser Himalayan series. They're also about 1.5 billion years old, so they're all Proterozoic. So if we think back to the very beginning, Strachey had these 3 different units. Now we've worked out where they came from and what their characteristics were. The Tethyan Himalayan series is a Phanerozoic succession, whilst the Greater Himalayan and the Lesser Himalayan, which are metamorphosed, came from the hinterland of Gondwana land. And they have experienced the most incredibly complex history of multiple orogenic events, the latest one being the Himalayan one. That's why I didn't start with those rocks. I thought we'd start somewhere else in the story. And now I'm going to show you an animation or snapshots from an animation of what we understand happened in the closure of this ancient ocean. So those ammonites I just talked to you about, they all came from this margin of Gondwana and belong to have affinities with that Tethyan realm. This is the Jurassic. Those ammonites were Jurassic. Now we get to the early Cretaceous, and India and Madagascar have broken away from Africa. Africa's broken away from South America, and lots going on around here as well. And you'll see that at this time, sea level was very high, and you had a seaway across Africa, and you had large flooded continental shelves. Later in the Cretaceous, India has broken away from Madagascar and starts an incredible northward journey. I say incredible because it was moving at an exceptionally fast rate of 180 millimeters per year. 18 centimeters a year doesn't seem much, does it? It's no other continent is known to have moved so fast. To the early Eocene, we haven't, and it's 50 million years. Now, I don't quite agree with this animation because in my work, it's fairly obvious that collision has already taken place, but it's a minor point. So about this time, there was a slow motion car crash. You have to think of India being a car coming up on the inside lane rather fast, and there's another car in front of it going along in the inside lane, but not so fast. And you get a slow motion car crash because this Asia is moving northwards as well as India. And perhaps you can see that if I go back. So, but India's moving much faster. So you get the collision. And now we get to the late Eocene. Collisions occurred. The Tibetan plateau is rising up. More high land to the north of India. And this northern area of the Indian continental shelf is concertinaing, collapsing, falling in on itself. And we get to the present day where the rate of uplift of the mountain chain is about 10 millimeters a year, balanced by equivalent erosion. And the rate of, but convergence continues. That's the extraordinary thing. One tends to imagine that if you have continent-continent collision, then you get a suturing of the two continents and you get no more plate movement. Plate movement shifts to some other plate boundary around the world. Well, that's not what happened here. It slowed down, but India's still moving northwards towards Asia. The contraction that's occurred so far is estimated at 1,000 kilometers. It's a major contraction. So now we come to the next part of the story, and it's to look at the collision zone. This is the collision zone here. It's at the north end of the Himalayan series. We're now getting familiar with these, the Lesser Himalayan, Greater Himalayan, Tethyan Himalayan series. We've looked at them all. But now, what happened where you had this collision? Well, we have to go back to before the collision, which was at 50 million years ago. That's just in the early Eocene. And think about what was happening before. So in that collision zone, which is a zone about 10 kilometers wide, you've got rocks of an age from Triassic right through to late Cretaceous, even into the Paleocene. And they consist of volcanics, of ophiolites, and a whole suite of basic and ultra-basic rocks, which all have oceanic affinities. So what we're seeing in this collision zone is what was within the Tethyan Ocean. And the diagram I showed you before the Tethyan Ocean was a simplification because you had two ocean you had two subduction zones within the ocean, one against the Spong arc and once against the Dras arc. And these volcanic arcs all got compressed together and accreted onto Asia. And so here we are at 56, so this is more or less at the time of the collision. And you can see that some of these oceanic arcs, island arcs, are being forced out southwards on south-verging thrust plains. And so let me tell you about the Mariana Arc. It's the deepest subduction zone anywhere in the world, and it's as deep below sea level as Everest is above sea level. An extraordinary subduction zone creating an island arc. And because I always put north on the right-hand side, I've switched that round so that this is analogous. This Mariana Arc is analogous to one of these arcs, particularly this one here, the Nindam formation and the Dras Arc. So this is how the Dras Arc formed. Oceanic crust subducted beneath oceanic crust, creating a suite of basic and ultra-basic rocks. One interesting thing was the Spong Arc shot up onto the continent of India and landed on the top of the Tethyan Himalayan series, where you can go and study the ophiolites sitting above Cretaceous limestones. Just to show you some rocks from the suture zone, on the north side of the suture zone, Ganser went and found ophiolites. These basic rocks, when they're weathered, they normally turn to serpentinites, beautiful green serpentinites, and that's what we have here, which he recognized as being evidence of ophiolites. And he defined this major fold and thrust as the great counter thrust, which is mapped out here. This is a different thrust to the ones we've looked at before because it's on the north side of the suture zones. We're on the Asian side of the story now. And here they are, deep green colored rocks, serpentinites, and basic igneous rocks which have weathered badly to these rusty colors. And here, going along the Tsangpo River, which follows the line of the suture zone, you can see these weathered ophiolites. One other thing that you get, which is really interesting along the suture zone, are eclogites. And these are very pretty rocks. These garnets here, we've got, it's all written out here, green omphacite pyroxenes, and you've got glaucophane, blue glaucophane in there. There's a thin section of this eclogite. It weathers black, and it's been down to about 80 kilometers below the surface on a thrust, and then perhaps as a result of slab break-off, which we'll come to later, has come back up to the surface. And so this is a feature. These are ultra-high pressure rocks and are typical of suture zones. So just a few more words about this Asian block, where you have a Ladakh batholith and the Karakoram batholith. They formed in the same way that the rocks are forming today in the Andes. As a result of subduction, this we can imagine as the Tethys Ocean being subducted beneath the Asian continent. And you get andesitic volcanics at the surface, and you get granites at depth. And that's exactly what we have in the Ladakh batholith. And it's similar in the Karakoram batholith. And I think we'll skip all those words. These are some landscapes from the Asian bloc. Dramatic scenery up in Ladakh, in the northern part of India, Tibet just across the border, Bactrian camels, beautiful lake, the largest high-altitude lake in India, and it's an endorheic lake. It means that water can't escape. There is no outlet from the lake. And yet, ironically, it's not particularly saline. So now we're going to come back to what happened in the main part of the mountain chain. Because I've taken you on a tour so far, right from the Swalicks in the south to the Asian block. I've shown you how this lot came from the south to collide with this in the north. But what happened when the collision took place from 50 million years onwards? Well, we'll call it the Indian fragment because it's a continental fragment that's broken away from Gondwana. On the northern margin of the Indian fragment, you had this passive margin full of sediments which can be as thick as some 20 kilometers of section. And this is what it looked like with the continental shelf, the rise, the slope and the rise. If you do sandbox modeling and you establish some layers of white and blue sand and then squeeze it from the right-hand side, this is what happens. And when you've got 30% closure, you get folds. And when you've got 44% contraction, I should have said, you get thrusts. So the fold breaks and you get a thrust coming up out of the focus point. And that's exactly what you see in the mountain chain. This is a picture taken by Mike Searle in Ladakh, some kilometre high, 1,000 meters, great fold, matching some of the folds that you could see in the sandbox. And now let's look at some of the thrusts that you can see. Well, this is a modelling of thrusts. And the way it works is that firstly you get a break and you get this horse rising up here. We call them horses. The next one, you get a break here, and the second thrust sheet is that. And the third thrust sheet is this one. And in short, the mountain chain is built up of a great stack of thrust sheets, as illustrated in this theoretical model. And this is also a model, but it's based upon the actual rocks and thrusts that you see in the lesser Himalayan series. This is the greater Himalayan series, and this is the Tethyan, but most of this is lesser Himalayan. And here's a model starting off with everything flat, and you get one thrust sheet, another one coming up underneath it, and so on. It's far too much to explain. You just get the general picture that you're stacking up thrust sheets. You're also getting a lot of erosion away. Of what rises up is eroded away. But remember what we said here, that for every 1 meter you put on top, because of isostasy, you've got to put another 7 meters down below. People sometimes say, could Everest be much higher? Might it have been much higher? Well, it's 9 kilometers above the surface, so you have to have 80 kilometers below. There's a limiting point to how thick you can make that route of the mountain chain. Mountain chains are complicated places. And because I always put north on the right, these have been reversed. But this is the Rockies. Look at this great collection of thrusts. And as I say, those drawing these diagrams have been concerned primarily to map out the thrusts. But we should remember there's a deep root underneath both of these mountains, the Rockies and the Cantabrian Mountains in Spain. Now, this collision, it didn't happen gently. It didn't happen gradually over time. It happened episodically. You build up tremendous tension on these thrusts, and eventually that tension gives, and you get an earthquake. You get a movement on the thrust. Now, here's the main Himalayan thrust. This was responsible for the Gorkha earthquake of 2015. The movement was about 1 meter, just 1 meter, enough to shake the whole mountain chain. Well, that's an exaggeration, but the whole of that region of west central Nepal. And it caused some parts of the Himalayas to rise up quite significantly, perhaps 0.5 meter. But actually in some other places you saw the surface decline. And so these movements take place in a very complicated way and episodically, and at an interval of about every 800 years. You can work out statistically and from records that there's a sort of periodicity of about 800 years in the Himalayas. That's not a universal rule for other mountains. Now, how are we doing for time? 5 to 9. Okay, are you still awake? Yeah, good. Well, it's a good thing, because now we get to a really surprising bit of the story. This is Mike Searle's cross-section up through the Kali Gandaki, up to Dhaulagiri, you remember that? And he went all these different colours, what do they mean? Here we've got the metamorphic index minerals. Do you remember this chart from textbooks? They're the index minerals of metamorphism. Can't read it, can you? But you start with biotite, and then you get garnet, and then you get kyanite, and then staurolite, and then sillimanite. And you're going, each one of those is an index mineral for a higher stage of metamorphism. And once you get to rocks with sillimanite in, they're pretty well melting. Here we're going up the section. These rocks are not upside down. You start with biotite, metamorphic rocks, then the index mineral for the next one is garnet, then the index mineral is kyanite, and then it's sillimanite. It's the opposite of what you should get. As you go up section, you should get to lower grade metamorphic rocks, because generally speaking, your heating from the top downwards gets hotter as you go down. So how could this happen? It was not understood for years, and because you've got a whole series of thrusts, it's plausible in your mind to imagine that you've just thrust rocks of different types against each other and created a rather anomalous metamorphic story. But there's a better way of explaining it than that. I think this was recognized by Ganser back in the 1930s and reported. I mean, it had a name, inverted metamorphic gradients, but how did they happen? Well, as you go up through these rocks, I just must show you what the upper unit of the Greater Himalayan series looks like. You've got partial melting here. You've got, as in all gneisses, you've got compositional segregation. They're not exactly melted, but they're moving in that direction. Tigmatic folds here. And then you get to the position where the rock has melted. This crustal rock has melted, and it produces a particular type of granite. It's very strong in silica. It's got white feldspars. It's got lots of tourmalines, these lovely black tourmalines. You also get some muscovite and some garnet. It's called a leucogranite. Leuco means white, so it's a white granite. And it's very distinctive. It's the product of the melting of crust, of continental crust. Continental crust having a lot of silica in it. The picture is of the northern end of Manaslu, which lies to the east of the Annapurna Mountains, and you've got 200 to 300 meters of this white granite. It tends to cross the foliation. Here's a foliated gneiss in Bhutan, and you can see this leucosome, as we call it, crossing these foliations, but very much a part of the continental crust. And it was Mike Searle who worked out why you got these inverted metamorphic gradients. And I was with him a year and a half ago in Mustang. So here we are. This is the Mustang region of northern central Nepal. China, Tibet's just up there. And this is how it works. The Greater Himalayan, this is a very simplified model. The Greater Himalayan series has the highest grade metamorphic rocks, and the stress regime on these molten rocks is indicated by these arrows. And because of that stress regime, the granites, the molten granites, begin to flow. And it's called channel flow because this is the channel, these are the boundaries of the channel. And these granites are moving, and they're moving in response to the prevailing stress regime. So they're not going to go to the right because you can't go uphill to the right or up to lower pressures. You can if you go to the left, to the south. And so here are arrows indicating the movement of these granites up towards the surface. Now, if you imagine what's happening there at this South Tibetan detachment, I may not have used that phrase before, but it's that abnormal normal fault, which is a low-angle normal fault. What's happening is that these rocks beneath it are moving upwards and southwards, and it's called channel flow, and it solves the problem of how... No, sorry, one more thing. These rocks, these Greater Himalayan series rocks, have some uranium-rich beds within them, and that produces a heating source. So you have to ask why in this diagram is that cooking pot, I call it a cooking pot, why is it there and not higher up or lower down? It's because within that succession you've got some uranium-rich rocks which are providing a heating source. So you get a cooking pot here. You get channel flow that way. And what happens below the cooking pot? What happens is that it gets cooler downwards. So it's hottest there, and it gets cooler upwards and cooler downwards. Well, a cooler downwards gradient would explain the inverted metamorphic gradients. And that is what's proposed. This explains it in more detail, and I'll just show you with these little bubbles. So here's your mid-crustal cooking pot, uranium-rich shales, and the movement is in that direction. A southward and upward extrusion of these magmatic rocks, these crustal melt rocks. And here beneath that, you've got inverted metamorphic gradients. And above it, in the rocks that are just above the abnormal normal fault, you've got a great chaos of folded rocks, where, as I mentioned, a lot of the thrust is sort of verging to the north rather than verging to the south, which all of these rocks are doing. This is from Parsons, who was one of Mike Searle's research students. And so I thought I'd show you a few pictures now. These high-grade metamorphic rocks are best studied if you go to the top of Kanchenjunga, which is the third highest mountain in the world, and visible from Darjeeling, but also in this case from Sikkim. And my wife and I went there some years ago and got up very early in the morning, and the sun rose on the top, picking up the colours of those high-grade metamorphic rocks of the Greater Himalayan series. And the last picture here in this sequence has these little dots on it. They're reflective tags on the top of the tents that we had slept in for far too few hours So there's a tent. Perhaps you can just see, or perhaps you can't. So I haven't shown you a geological map of the Himalayas yet, and it's quite deliberate because it's the most complicated thing you could find. But I'll try and help you a bit with it. Here is a geological map. Pakistan here, right the way down to Myanmar. And it's really divided into three things. The Himalayan series, which came from Gondwana, that's these colours, going to green. Green's the Tethyan Himalayan series, Tethyan based on the ancient ocean of Tethys. Then on the other side, you've got the Eurasian block. And that block acted like a buttress because it's full of granites and of basic igneous rocks, a very solid block on the north side. And between the two, you've got the volcanic rocks of the suture zone. I put on here just the places I've talked about. This is Kachenjunga here, just north of Darjeeling. Here's Kathmandu. Here's the Annapurna Mountains. I mentioned Dhaulagiri quite a few times, and Mustang. And then further along, this is where Richard Strachey did his cross-section, up to Mount Kailash, which is there, the holy mountain of Tibet. And I mentioned it's about 200 miles transect. And then here, I showed you repeatedly a section through Kashmir and Ladakh because it was the most useful one to show, to illustrate these points. And that's there. So I should finish really, to be comprehensive, I should just tell you about some of the rocks that were deposited after the collision. So the post-collision deposits, we mentioned the Sewaliks already, shed from the uprising mountain chain, producing fluvial sandstones on the south side. And then the suture zone, it's a bit more complicated than I said. It's not just all those volcanics. You've got a big basin developed there, rather oddly, right along the line of what is now the Indus River and the Yarlung Tsangpo River sit right above this suture zone, and you've got a thing called the Indus Basin. And it's filled with sandstones which have been deformed because they were filled and deformed as the mountain continued to be active and to grow. We can't talk about post-orogenic deposits because it's still an active orogenic zone. And here's an example. These are the Indus Basin sandstones, nearly vertical, tipped up. Here are Indus Basin sandstones in Mount Kailash, nearly horizontal. And here, a whole series of names for these Indus Basin rocks. And very late Quaternary intramontane alluvial and lacustrine deposits have developed around Kathmandu and around in Kashmir and in here the Takola Graben. These are problematic in Kathmandu because you've got these soft lacustrine deposits and all the buildings have been built on them. And when you have an earthquake, you shake. Those lacustrine deposits, recent deposits, don't make very good foundations. So it's a bit of a problem. The sediment that's being eroded from the mountain chain is transported in some of the great rivers of the world. The Yarlung Tsangpo Brahmaputra. It's got three names because it was thought once that it wasn't all one river. It's on the north side of the mountain chain that cuts through and joins the Brahmaputra. The Indus flows the other way, north up here and then down to Karachi. They shed sediment into the ocean, the Arabian Sea, and the Bengal, the Bay of Bengal. But so let's look at the Bengal fan. It extends here some 2,000 to 3,000 1,000 kilometers out into the ocean, and they're transported by turbidity flows. And the flow starts here, and it flows, and it flows, and it flows, and flows. It goes right the way through and builds up this great pile of turbidites on the ocean floor. It's one of the most dramatic sediment piles anywhere in the world, and it's been transported there by the Yarlung Tsangpo River out into the Bengal Fan, and also by the Ganges River. And then you've got a comparable thing here, the Indus Fan in the Indian Ocean, Arabian Sea. Finally, and it really is finally, why is the Tibet plateau still so high? It ought naturally to have subsided. It's 50 million years old, and yet it's still up there. And this diagram from the Tectonics Observatory from Caltech suggests what happened, that the continental crust from India, under thrusting the mountains and the Tibetan plateau, saw what we call slab break-off. The downgoing plate or slab in the subduction zone has broken off, and it's partly because what you're trying to force down is continental crust, not oceanic crust, and it's relatively light. So you've got break-off there, and you've got under-thrusting of the Tibetan plateau. Now, there's another way of looking at this. You can say the Indian continental crust decouples and splits into an upper and lower lithosphere, and the upper portion is under thrusting the Tibetan plateau, and the lower slab is being subducted, so you've got a normal subduction zone. Only tomography and will sort that out, and I don't think that really we have the answer yet. So I've taken you on a tour, and we started with a view of the mountain chain and the main frontal thrust and the Sewaliks, and we've gone through these Himalayan series rocks. I described them twice, once roughly what they were in historical terms, and then later how they formed in those sandbox diagrams. And then we got to the suture zone, full of compressed, crunched up oceanic material between these two great blocks. The Eurasian block being rather more of a buttress, so that all the crumpling took place in these rocks, which were derived from Gondwana. And then we get to the Tibetan plateau, and it being high, and that's the end. Thank you.
Thank you very much. That was extraordinary. So many